Suppose you have a scatter of points, say customer locations, and you want to see how they group. With a method like k-means, the very first thing it demands is a number. How many clusters k? But what if you don't know? What if the honest answer is, it depends how closely you look? Hierarchical clustering refuses to pick k for you. Instead, it builds a whole family of clusterings at once, stacked inside a single tree, from every point on its own, all the way up to one giant cluster. Later, you decide whether 2, 3, or 4 groups make sense, just by choosing where to slice that tree. There are two ways to build that tree: bottom up, called agglomerative, and top down, called divisive. Divisive starts with everything in one lump and keeps splitting it. It's rarer. So we'll spend our time on the bottom up one, which is the workhorse you'll actually meet. Here is the whole recipe, and it fits in a sentence. Start with every point as its own tiny cluster. 5 points, 5 clusters. Then repeat one simple step. Find the two closest clusters and merge them into one. Closest here means A and B, so they join. Merge the next closest pair, and the next. The number of clusters ticks down by one each round. Keep going until just one cluster is left, holding everything. That sequence of merges is the entire algorithm. But that recipe hides one slippery word: closest. The distance between two single points is obvious. The distance between two clusters of points is not. Which points do you measure between? The rule you pick is called the linkage, and it quietly decides everything. Picture a green cluster and a gold one. Draw every link between a green point and a gold point, a whole web of possible distances. Linkage is simply which of these you call the distance between the clusters. Single linkage takes the minimum, the nearest pair. Complete linkage takes the maximum, the farthest pair. Average linkage takes the mean of all of them. And Ward's method picks the merge that increases the spread, the variance, the least. Why does the choice matter so much? Single linkage only needs one close pair to merge. So a trail of stepping stone points gets strung together into one long, straggly chain, even when the ends are miles apart. Complete linkage insists the farthest pair stay close, so it refuses to merge anything that would stretch a cluster out. The result is tight, round, compact clusters. Same points, same data, but the linkage alone can hand you completely different groups. All those mergers get recorded in one beautiful picture: the dendrogram, the star of this whole idea. Let me build one in front of you and teach you to read it. Read it. And you can read any hierarchical clustering at a glance. Along the bottom sit the individual points, each one a leaf of the tree. Up the side runs a scale of height, and height means distance. That vertical axis is the whole secret. When two clusters merge, we draw a bracket joining them. And here is the key: we draw it at the height equal to the distance at which they merged. P and Q are very close, so their bracket sits low, at height 1. R and S are a little farther apart, so their bracket is drawn higher, at height 2. Already the picture is telling you something. Low brackets are tight pairs, tall brackets are distant ones. Finally, the two pairs join, far up at height 6, because these two groups are genuinely far apart. And that's a complete dendrogram. Every leaf connected, each junction telling you exactly how far apart the two things it joins really were. Now the payoff. Slide a horizontal line across at some height and count the vertical branches it crosses. That many clusters. Cut here, between 2 and 6, and the line slices exactly two branches. P joined with Q on one side, R joined with S on the other. Two clusters. Let's do one completely by hand. 4 points A, B, C, and D. Using Manhattan distance, the sum of the horizontal and vertical gaps, and single linkage. There they are, A, B, and C huddled near the corner, D off on its own. First, every pairwise distance. A to B is one step across, distance 1. A to C is 2 steps up, 2. B to C is 1 across and 2 up, 3. And D is far from all of them. 10 from A, 9 from B, 8 from C. The smallest number in the whole table is 1, between A and B. So A and B merge first, at height 1, the lowest bracket in the tree. Now recompute under single linkage. The distance from cluster A to B to C is the nearest of the two, the minimum of 2 and 3, which is 2. So A to B and C merge next, at height 2. Finally, D joins. Its single linkage distance to the ABC cluster is the nearest of 10, 9, and 8. That's 8. So the last bracket is drawn away up at height 8. And D, the outlier, merges last of all. Here's the very tree we just built. The magic of a dendrogram is that you don't commit to a number of clusters while building it. You choose afterwards, with a single horizontal cut. Everything that has merged below the cut stays together. Anything that would only merge above it stays apart. Cut high, at height 5. Up between the merge at 2 and the merge at 8. It crosses just 2 branches, so 2 clusters, A, B, and C together, with D alone. That matches the I. D was always the odd one out. Drop the cut lower to height 1.5, between 1 and 2. Now it crosses 3 branches, A with B, then C by itself, and D by itself. 3 clusters. Lower the cut, more clusters, and cut right at the bottom, below every merge. And you're back to 4 singletons. Every point its own cluster. So one dendrogram quietly contains every clustering from one group up to n, and the cut height is the only dial you turn. One more example, to feel the linkages apart. 2 clusters, a green pair and a gold pair, sitting as the corners of a rectangle, 3 across and 4 tall, measured with ordinary straight line distance. The 2 short sides are length 3. The 2 diagonals are length 5. So the nearest cross pair is 3, the farthest is 5, and the average of 3, 5, 5, 3 is 4. So the very same 2 clusters sit at distance 3 under single linkage, 4 under average, and 5 under complete. Single always gives the smallest gap, complete the largest, average somewhere between, which is exactly why they can merge things in a different order. Your turn. Here's a fresh dendrogram of 5 points. Suppose you cut it straight across at height 4. How many clusters do you get, and which points end up together? Pause the video, trace the branches the line crosses, and I'll wait. Here's the answer. Draw the line at 4. It sails above the merges at 1, 1.5, and 3. But below the final merge at 6, it crosses exactly 2 branches. So 2 clusters. On the left, P, Q, and R have already joined below the line, so they're one group. On the right, S and T have joined, so they're the other. P, Q, R together and S, T together. If you saw that, you've truly got dendrograms. Trap 1. Forgetting you must fix 2 separate choices before you start. The distance metric, Euclidean or Manhattan, and the linkage. Single is the minimum, complete the maximum. Change either, and you can get a different tree and different clusters. Trap 2. Thinking linkage matters from step 1. It doesn't. When every cluster is still a single point, the minimum, maximum, and mean are all the same one number. Linkage only starts to bite once clusters hold more than 1 point. Trap 3. Cost. You need the distance between every pair of points, so memory and time grow like n squared. On a few thousand points, it's fine. On millions, it simply won't fit. Trap 4. It's greedy. Once 2 clusters merge, they stay merged. The algorithm never goes back and reconsiders. One unlucky early merge can quietly distort the whole tree above it. And trap 5, the same one that haunts every distance method, scale. A feature with a huge range swamps the distance and hijacks the clustering. Standardize your features first, always. Let's tie it all together. Agglomerative clustering starts with every point alone, repeatedly merges the two closest clusters, and stops when just one remains. No care required upfront. How close two clusters are depends on the linkage. Single takes the nearest pair and tends to chain. Complete takes the farthest and stays compact. Average takes the mean, and Ward keeps the variance low. Every merge is recorded in a dendrogram, where the golden rule is that a bracket's height equals the distance at which it merged. Tall means far apart. And to finally choose your clusters, you cut the tree at a height and read off however many branches you cross. One tree, every k, and the cut is the only decision left. That's the whole elegance of hierarchical clustering.